this is what I wanted. Okay, girls. All right, so do not write this down. It's one of those moments that I'm going to say just watch. Okay? Also, you need to watch for two reasons. One reason is to make sure I don't make a mistake in all of my arithmetic and algebra, so that we've got close to 20 people watching me. The other reason is that you'll vastly appreciate what you'll find out to do before your homework tonight, okay? So I'm going to do x plus, I guess y'all just start with something easy, to the sixth, okay? So you would go, well, I can definitely do that, but it's a lot more tedious probably than you imagine. That's why I say don't write this down, but please actively watch. I'm going to want you to notice some things. Good mathematicians, like on your job one day, you may not even major in math. Some of you will, or be engineers or whatever. But I'm sorry, I was just thinking lately, I've seen so many of my former students that are visiting New York, and almost all of them are engineers. But one, I'm going to Seattle next week, I hope, not to visit one of my former students, but I'm going to try to see her while I'm there, but she's an engineer with Starbucks. And she's like, they're working from home. Amazon's working from home. Twitter's working from home. Facebook's working from home. So anyway, you may actually have a math-related career, but even if you don't, which a lot of you I know won't, you'll be in business, you'll be in marketing, you'll be in sales, but you'll set yourself apart with your critical thinking skills. People will notice you're good at math in a hurry, and it can really promote you, or not really literally. I have a few stories I won't tell now just because it took so long to get started, but I have actual stories of people that were actually literally promoted because of their math skills. Like one guy, when I met him, I'll tell you one story if you beg. So I was introduced to this guy named James Plunkett, I think is his name. The reason that I'm going, I think is his name, even though like we've been on vacation with them before, but everybody calls him Rocket, like rocket scientist. And so I don't hardly ever hear his name. People call him Rocket. But this is all he did. And I should maybe wait and tell the story when we get to our exponents and logarithms unit. He, kind of fresh out of college, went to work in the banking industry. He majored in like finance of some sort, but he was really, really good in math. And so he was literally in a closet. Like he came to work like at the bank, and they're like, "Where are we going to put you?" And so they kind of cleaned out a closet and put a desk in there, and he was working in the closet. And he could overhear them trying to figure out how many years it would take for oh my goodness. So anyway, he overheard them talking about how many years it would take for something to a loan to mature or be paid off, or investment. I don't remember the thing, but it was like how much time it would take. And in a formula, when you're doing interest, you'll see this with me later this year, time usually ends up being an exponent because it's geometric progression. Y'all know what I mean? Like 3 to the x would make you go 3 to the first, 3 to the second. So anyway, I'll teach you all of that later. But while I'm talking about the story about being good at math is they were guessing and checking, and they couldn't figure out the exact number in their bank. They really needed to know the exact number to report to wherever they were going. And so he just sat in his office and put a logarithm on both sides, which allows you to bring the exponent down. Logarithms are to find exponents, like a square root's to find what you squared. So he took the logarithm of both sides, and he kind of tentatively showed it to his boss, and his boss was like, "Oh my gosh, you used a logarithm." I mean, he was just like, people really use those? And then they checked like the actual number that he had, like 42.85, I don't know what it was, and it was exactly what they were looking for. And they're like, "Let's clear you off a space out here." You know, by the time I met him, he was making like 6 figures, and they were like, "You could do everything." So it was, and he's like, all I did was use a logarithm. But anyway, so to go back to what I was saying, why I want you to watch me is I want you just to see what you notice as a mathematician. Whatever your job might be, you'll probably be the person that notices a pattern, something that can make things easier. Mathematicians, or most of the time employed because they're very efficient, or they set themselves aside because they're very efficient. They're very sure in what they're doing. They've checked it, they've proven that it will work, but they're more efficient. So you're just looking for a pattern so that you don't have to do what I'm doing right now, okay? All right, here we go. Well, that's not helpful. Okay, sorry. All right, so here we go. Ready? All right, so that's x squared plus xy is 2xy plus y squared. And I could take that times this x plus y, but I think I'll just notice that a pattern. I have 3 sets of those, so I think that will speed me up some instead of just going times each next one. So there we go, do a little bit of mathematician stuff there. 2xy plus y squared. So I thought that was pretty bright. And it does save some time instead of taking each product times the next product. Okay? All right. And do y'all realize that's one thing that's time consuming? You have to find that product. You have to keep a running total. Okay, now I'm going to do some more distribution. That's x to the 4th. That's 2x cubed y. That's x squared y squared. This one is 2x cubed y. 4x squared y squared, 2xy cubed. All right, now I didn't do everything yet. This one is x squared y squared. Can't read it anymore. 2xy cubed and y to the 4th. Now I think it would be smart before I take that product and multiply it times to see if there's any like terms. So I think I have an x to the 4th, 4x cubed y's, is that it? All right, so x squared y squared, I think I have 6 of those. And 4xy cubes. Do you see if you make a tiny error anywhere, it's all over? Okay, so that gives me x to the 6th. Uh, 2x to the 5th y. X to the 4th y squared. All right, this one is 4. X to the 5th y. 8x to the 4th y squared. Watch me. Am I okay so far? 4x cubed y cubed. I'm so sick of this already. 6x to the 4th y squared. Yet you're going to be asked to do this over and over again. 12x cubed y cubed. Good thing you have 2.5 weeks of spring break. 6. Thank you for laughing, Nicole. That was great. Okay. 6x squared y to the 4th. 4x cubed y cubed. Are y'all watching? Okay, y'all are watching. All right. 8x squared y to the 4th. Okay. So that was this one. I know. This is 4x y to the 5th. Then I have x squared y to the 4th. 2xy to the 5th, and I may have done everything, y to the 6th. Okay, now if you have 1, 2, 3, 4, 5 times 3 items, you should end up with 15 things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. Okay, so I have enough. At least they may not be right, but at least I have the right number. All right, like terms, x to the 6th, 2x to the 5th y. 4x to the 5th y. Any more? All right, 6x to the 5th y. All right, x to the fourth y squared. There's 1.
There's 8. 6.
Oh, wait, isn't this 9 so far?
Yeah.
9. Oh, and a 6 is 15. All right, so 15 of those. All right, so these are gone. All right, then I have x cubed, y cubes, 4. So that's 16, 20. Okay, these are gone. All right, then I have x squared, y to the fourth. I have 15 of those because this is 14 and 1 more.
Oh, wait.
All right, and then I have 6 x y to the 6th and a y to the 6th. Thank you. Finally made a mistake. Thank you for watching. Okay. So raise your hand if you notice some things. Let me pull that up so you can see it now. That is the correct product because I know the fast way to do it that I'm going to teach you, so I can kind of double check it.
Oh, it's reversed.
Oh, is it?
Yeah,
Okay, so raise your hand if you notice some things. All right, Katie?
Well, Elena just said it, but it goes.
Okay, Elena.
No, it's like 1, 6, 15, 20, 15, 6.
All right, so it goes up and then comes back down.
Exponents are. Yeah.
Okay,
5, 4, 2.
So Lily, what's happening?
The exponents are reversed too, so it's like y6, y5, y4.
Okay, so the y's are really growing, aren't they? And what are the x's doing? They're shrinking. Anybody notice it, Michaela? Yes, that's real important. This is adds to 6. This is a 5 and a 1 is 6. 4 and a 2 is 6, which is what I started for way up there. So 3 and 3, 2 and 4. So you're noticing some things right away. Wouldn't it be nice to know how to create those numbers in the front? Because I think, if I did x plus y to the 7th, which I'm not going to do, that it's going to be that much worse. What if I did x plus y to the 7th? What do you think it would start and end with? X to the 7th and end with y to the 7th. What do you think if it starts with x to the 7th, the next x will be? 7, 6, 5, 4, 3, 2, 1. And then the y's would grow. Then you could double check Michaela and make sure that you had a 5 and a 2 and a 2 and a 5 to make a 7. But we still don't know how we get these numbers. Katie and Elena, the numbers will go up and come back down. Almost, if it's a very simple one. If I do something like x plus 2y to the 5th or 6th or whatever I did, you wouldn't have noticed this pattern I wanted you to see. So it does happen, but it can kind of trick you sometimes. So let me show you what we're going to do. Let's do it this way. Let's go x plus y to the 6th, and let's take into account your patterns. Now, when I first started teaching this, like the first day I ever taught it, probably in Algebra 2 in the 1900s, I would go x to the 6th, x to the 5th, x to the 4th, ready to show them this super cool thing. And I would run out of room as I was building it. And so I've started doing it vertically and write it horizontally later. So if you wonder why I'm writing it vertically, it's only because I would then find myself squeezing in plus signs and numbers and stuff. Okay? By the way, there's a formula that I will pull up and show you in your book and all over online. What I'm showing you right now is the binomial theorem. And a lot of real life application that we'll also look at. But also, this is just something that I would say as a mathematician that not just I, but lots of people notice. Like my teacher taught me the binomial theorem, which it looks kind of treacherous. I'll show it to you first. And I could apply it, but I'm like, oh, what if it's really ugly looking. And so I'll show you a pattern that I just used to crank these out. Some of you have already done this. Maybe you did it in Algebra 2. Some people do this with Pascal's triangle, which I'll also address. I just don't personally use Pascal's triangle, but I sort of kind of do. So you probably did it in Algebra 2. So it might sound familiar, okay? We'll expand on it, literally.
All right, so there's one of them. Let's see. Where's another good one? There's different ways to write it. I want the one with the C in it. All right, let's just look at these two. Okay,
In our book, they actually don't have, in our book, don't have this written or this written. They sort of have this one. There's a few different ways to write this notation, and I think you may have studied permutations and combinations a little bit. No, yes? Okay, I'll pretend like you haven't, and maybe you haven't. There's something called a combination and a permutation, which we're going to super study. That's why we're doing this binomial theorem, even if you've seen what I'm about to do in Algebra 2. Like I said, we'll build on it. Use permutations and combinations as part of what's called counting principles. Like, people are actively looking at the percentages and probability and mortality rate and all that of the coronavirus right now. You may, want to know your probability of many things, like whether you entered a lottery to go to Hamilton like I do every day and don't win. So there's all sorts of counting principles. One way to count things is actually with a permutation of like 5 things, 3 at a time, okay? Like for instance, let's take the word bead, okay? And hopefully, I shouldn't pick a 4-letter word because Lord only knows what I'll spell, but let's just hope everything's going to be okay. I'm not trying to spell real words. I'm just seeing how many arrangements I can get here. Have y'all done this? Okay. There's a lot of, okay. B, E, D, A, B, A, D, E, B, A, E, D, B, D, E, A, B, D, A, E. Can you think of any more with B in the front? Okay, I think that's it. Well, I would be bad at it if I didn't organize it and just make sure I just sort of stick with what I'm doing. So now, yeah, and so now as a mathematician, you're sort of looking, can I shortcut this because it's going to be tedious?
Yeah.
So I'm going to let E be first, E, B, A, D, E, B, D, A, E, D, yeah. How many are there? There's 24. Every time,
It's like there's 4 spaces.
you could do that, yeah. So 1, 2, 3, 4. There's 4 spaces. How many choices do you have for the first letter? A B, E, A, or D, right? So 4 spaces. And once I've decided on B, how many choices do I have for my next letter? 3. Time out, girls, because I want you to understand it. I don't want you just to do it. Like, where did this come from is this. Okay, so B, E, A, D. Any of those could be the first letter. After you choose B, couldn't it be A, E, and D? It didn't matter what order I wrote those in, by the way. After you choose A, couldn't you use D or E? But after you choose D, you could only use E. After you choose E, you could only use D. On this one, if you've chosen B and E, how many choices do you have? A and D. And this one would lead you to D, and this one would lead you to A. This one, E and A. This would lead you to A, and this would lead you to E. 1, 2, 3, 4, 5, 6. Girls, that's called a probability tree. And it really lets you see where maybe your SAT tutor came up with this, okay? And they may have explained it to you, but that's really not their job. Their job is you to pay them lots of money and you make a better score on the SAT. My job is to make sure you understand what you're doing so that you can do other things that aren't like this. Okay? Because it doesn't work if I had used something like, all I can think of is bomb. I don't want to use a bomb. And dead.
Tree.
I don't want to use dead.
So,
Tree, thank you.
But tree is two E's.
Okay, yeah. So there's like, if you have repetition, things are different. Girls. Hey, thank you for playing, but let me talk, okay? Glad you're interested. Once you have done this, it's very convincing that it's going to happen with the other 4. Why do all of that? So there's 6 this way, 6 with the E, 6 with the A, 6 with the D, 6 plus 6 plus, there's 24, okay? You're looking for a pattern. So on the other slide, what you were saying is how a lot of times math teachers write choices in little blanks. And you see how many choices do I have for the first letter would be 4. Once I've chosen that letter, whichever one it might be, how many do I have? 3. The reason I'm multiplying is you see it's going to happen these 4 times. That's why I'm multiplying. Wouldn't this column, if I kept writing it, have 12 choices in it?
Yeah.
Okay? And then I want to multiply all of those times the next column. So after you choose those, how many choices do you have? 2. And then once you've gotten a B, a D, and an A, you only have 1 choice. That's called a permutation, okay? That's a permutation of 4 things, 4 at a time, actually. And we'll get to what all that means in a minute. 4 times 3 times 2 times 1 is 24. So you've got to be able to count the ways something can be done before we ever branch into probability. And that's the easiest way to count. There's all sorts of other things that we're going to have to do, okay? So let's do another one.
So is that where the factorial is going to come in?
Oh, yes. And so you could call that 4 factorial. Yes, yes, yes. So that's where factorial like really comes in real life. People use it in many formulas. What if I have B and I'm only going to take 2 letters at a time? I could do BE, BA, BD. Hang on. Well, maybe not just because there's 2 though. Because if I had more letters, it would be different. So it just happens to be let's just wait and see. Okay, but good guess. BE, BA, BD. Anything else with B's? If I'm doing 2? All right, so EB, EA. I'm kind of convinced that there's going to be how many of these? 4, how many times?
Oh, 4.
So it'll be 12. And so it's just coincidence because I went from 4 to 2. So don't just think it's always half of it. Okay, it would be different if I'd done 3. But anyway, how you're going to do this is you're going to go, that's a permutation of 4 things 2 at a time. What that means is you're going to have, this is an N and this is an R. So you have N factorial over N minus R factorial. So you take the number of letters or whatever it is you're trying to do, and you have 4 factorial. And then you take 4 minus 2, which is 2 factorial. So you have 4, 3, 2, 1 over 2, 1. And these cancel out, and you get 12 ways. Which is fantastic to realize that really works. If I'm doing something big like a lottery or whatever, and I have, I say choose 8 numbers. But you're going to choose like 3-letter patterns of your 8 letters. And so you're taking a permutation of 8 things 3 at a time. Because I can guarantee you if I add 1 more letter, it gets that much more cumbersome. It jumps from 24 to 120 that I don't want to write on the board. Okay? And so that's a permutation. A permutation is where order matters. Like if my code is BED and your code is BDE, it's a different code. I can't unlock your computer with my code. Those are different. Order matters, okay? A combination is where order doesn't matter, which is ironic, okay? Because we say combination And if this was my locker combination, 4321, the order would definitely matter. I can't go, oh, and we've all done that, haven't we? Where we had a 4-digit number for a code and we think, oh, I know it's got like, you know, a 4, a 2, a 6, and a 7, but I don't remember what order. I can be putting a code in downstairs in the copy machine, and I do it sometimes. I'm like, I can't remember. I won't put it to you in case you jump onto the copy machine someday. But I'm like, oh, I get those numbers mixed up sometimes. It's not 5832, but sometimes I go 5382, and it won't work. It's none of those, by the way. But do you see what I mean? So it's funny when we say combination, we really mean permutation. You should go, I'm gonna, what's my locker permutation? What is my bike? Combination is really your bike permutation if you have a bike lock on your bicycle. So it's kind of ironic. A combination is the order doesn't matter. It would be like if Miss Alvar stepped in and said, I need 3 students to help me show some people around, okay? And I said, okay, well, why don't Michaela, Zaina, and Brianna help out? Oh, no, I changed my mind. I want Brianna, Michaela, and Zaina. No, never mind. I want Michaela. I mean, she'd be going, maybe you should go find somewhere else to work, okay? Because those are the same 3 girls. It doesn't matter what order I say that in. Do y'all see what I mean? Okay? The name, the way in which I name who's in my pre-calculus class, and so somebody asks me to do an alphabetical order, I just start listing them. Sometimes somebody says, who's in your honors class? And I just start listing as many names as I can. I actually have y'all in a group email, but my pre-calc class only has 10 students, and I've just never set up a group email. And so it doesn't matter what order I think of them in. You know, I'm still going to be able to send them the email. Okay, that's a combination of people.
That's such a fun
Okay.
class size.
Yeah. So a combination order does not matter.
You got more than double that.
So if I take the letters bed, okay, how many, I don't want to do bead. So if I take bed, how many ways are there to arrange the letters well, we'll take bead. I need more. Hey, Lily and Danielle, y'all be quiet. How many ways are there to arrange those letters and say those stand for people's names? Like, whose name in here starts with a B besides mine? Oh, Brianna. Okay, Brianna, Elena, who's an A? Is there an A in here? Okay, so we'll say Anne and Danielle, okay? So, do we really not have any A's? Okay, so anyway. I could so we're going to put them in a group to pretend like we're going to work on something in groups of 2. So I can put Brianna with Elena. Could I put Elena with Brianna? It's the same group, okay? So we're doing a combination right now. So I could put Brianna with whoever Ann is. I could put Brianna with Danielle. All right, so I could put what? Anything else?
Yeah.
All right, so let's do Elena without Brianna, because Brianna said no. Okay, so Elena with Ann and Elena with Danielle. Or I could put Ann with, has Ann already been paired with Brianna?
Yes. Yeah.
Has Ann been paired with Elena? So I could pair Ann with Danielle. Has Danielle been paired with everybody?
Yes.
Are there any more?
No.
Okay, so do you see it's different? Are there less ways when order doesn't matter or more ways? Less. How many did we get? 6. All right, this is a combination of 4 things 2 at a time. If I was doing a permutation of 4 things 2 at a time, I would have more because wouldn't these 2 be different? Okay, remember we got 12? All right, because that would be 4 factorial over 4 minus 2, which is 2 factorial. That was 4, 3, 2, 1 over 2, 1, and we got 12. A combination where we're just putting things into groups, committees, teams, squad, all of those things are your key words that you're doing a combination. Like who's on the volleyball team. It doesn't matter what order you tell me, okay? So anyway, the way to do this is you say n factorial over n minus r factorial, And then you divide it by r factorial, and what that does is that just like cycles out all the switching. All right, let's see what that means. 4 factorial over 2 factorial, 2 factorial. Where did I get those numbers? There's lots of 4s and 2s swimming around. 4 factorial goes on the top. 4 minus 2 is this part. And then I have just 2 factorial. We'll do another one after this, but let's see if we're right. 4, 3, 2, 1 over 2, 1, 2, 1. Cancel, and 12 divided by 2 is 6. It works, right? Because we don't want to keep doing this because we know things are going to get way bigger when it really matters. Okay? So let's compare a P83 with a C83. This is a permutation, order matters. This is a combination, the order doesn't matter. All right, so this is going to be 8 factorial over what?
5.
Right, you subtract them, and 8 minus 3 is 5 factorial. It's just n minus r factorial. So this one's 8, 7, 6. What happened to 5, 4, 3, 2, 1?
I think it just
Cancels out. And so I think you all know where the factorial key is on your calculator, but many times it's bad to punch it because your calculator might go into overflow trying to figure out 20 factorial over 19 factorial is just 20. I don't need to put it in my calculator. I don't know what that is. 42 times 8. 256, I hope. No. 336, I believe.
Yes.
Okay. Okay, this one is going to be 8 factorial, Elena, over 5 factorial with an extra 3 factorial. What this does, if you got groups of 3, is it takes out all the different ways you could switch those 3. It divides it out. All right, so this is 8, 7, 6. What happens to 5, 4, 3, 2, 1? Over 3, 2, 1. So there's only 56 ways to do it if order doesn't matter. So if I was going to take our class of 20 and put you into groups of 4, I could check how many ways I could do that. Because in a group, the order doesn't matter. Okay? All right, so a club is a combination. The officers in your club are a permutation. Because order would matter if you're listing president, vice president, secretary. We're going to study that heavy duty later, okay, in a fun way. But the reason I did that is a lot of times in the binomial theorem, going back to this slide, you actually see this notation. In our book, it actually uses this. It'll have C, N, R, and then C, N minus 1 with like some, I don't remember exactly how the notation goes because I don't actually use it. I'll show you what I use. But it's got like a little notation that means the same thing. Do y'all see what I mean? Okay, so that's what we've been doing on that other slide. These are actually, when I look at them, these are some sort of combinations that are descending with the n, n minus 1, n minus 2, all the way down to you don't even have one at all. And do y'all notice that the second part is growing? So all those counting principles have something to do with multiplying out binomials. It's called binomial theorem, by the way, it's a good reason. I never told you that. It's x plus y to the like 6, a plus b to the 7th. We're expanding binomials to things with 2 items in them, 2 terms. So you'll see in our book, instead of this factorial notation, it's just shorter from to write it as C N R, where you have n, then you have n minus 1, then you have n minus 2. But that would be your bottom number, so I've written that wrong. So it has to happen over here. Let me find one. I've got it right here. This is how it's written. So let me write it correctly. Okay, so in our book, the binomial theorem is written this way. It has x to the n plus n, that's a plus,
n x to the n minus 1 y plus dot 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 plus c. This has n r x to the n minus r y to the r dot dot dot. And they just keep writing these down, these combinations. And so you could do that. That's what I did. I learned it with combinations after my teacher taught me that quick little lesson I just showed you. And I kept using like a C83 and a C82 and a C81 and, you know, counted it down. However, I noticed a pattern that will always get me there. So this is what I do instead of the formula, okay? So, and I'm sorry, I'm not really doing this instead of the formula. This is how I use that formula. So I'm going to do x plus y to the 6th. You ready? All right, you've noticed the pattern, x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, x to the 0. At the last one, we've done it a long time ago now, like 30 minutes ago, where did y'all notice it had an x to the 6th at the beginning and a y to the 6th at the end? You notice the y's were ascending while the x's were descending in exponent. So the y's are growing, y to the 0, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, y to the 6th. Now we need our coefficients. The first and last coefficient is going to always be a 1. And then I'm going to do a combination. But my combination is going to be this number, always, 6 factorial, over these two numbers have already been decided for me if you actually look in the formula. So I'm kind of cheating, but I think it's kind of smart. Those are the n's and the r's. So this is going to be 5 factorial. Remember, it had an n minus 1 in it? Okay, 5 factorial, 1 factorial. This one's going to be 6 factorial over what? 4 factorial, 2 factorial. It's already been decided for you, so your numbers are sitting right there. You don't need a formula, but you are using the formula. This one's 6 factorial over what? 3 factorial, 3 factorial. And this one is 6 factorial over 2 factorial, 4 factorial. And 6 factorial over 1 factorial, 5 factorial. So let's write down this one is x to the 6th. Would y'all agree? All right, 6 factorial over 5 factorial. Are y'all okay with that just being 6? By the way, 1 factorial is just 1. So this first one is 6 times 5, 4, 3, 2, 1. Doesn't that all cancel out? So this one's 6. X to the 5th, y. And isn't this one also 6? 5, 1, 1, 5 doesn't matter. It's commutative if y'all remember that word. So this is 6, x to the 1st, y to the 5th. This one is y to the 6th. Let's figure out this one. 6, 5, 4, 3, 2, 1 cancels over 2, 1. Do y'all remember that number 15 that cropped up? 30 over 2 is 15. X to the 4th, y squared. And isn't this one 15? But you're already kind of looking for it to go up and come back down because you already noticed that. You might remember the middle one. 20. All right, this one is 6, 5, 4. This 3, 2, 1 cancels, and I have another 3, 2, 1. That 6 is gone, Katie. We're left with 20. 20x cubed, y cubed. Then you can write them out in a string. X to the 6, 6x to the 5th, y. 15x to the 4th, y squared. 20x cubed, y cubed. 15x squared, y to the 4th. 6xy to the 5th plus y to the 6th. I'm sure some teachers don't walk in the room first and do this. And I don't blame them. I doubt, I mean, maybe some do. I bet a lot do, but some would maybe ought not to do all of that, right? Okay? But the reason I did it is because this at first might look like, oh, that's tedious, but in comparison to the first slide, wouldn't you much rather do this cute little thing, okay? So let's do another one together. Don't do it yourself, we don't have time. Okay, so what if I'm gonna do, I'm gonna do two kind of quick ones just to get the process down. What if I had a plus b to the 8th? you would want to like scream, I hope, if you had to actually do that. So don't forget you have the binomial theorem, okay? All right, so it's going to start off a to the 8th. I always get these first because then it means, girls, if I go in and get this combo of the variables first, you see the exponents have already decided the numbers on the bottom for me, so I don't need a fancy formula with all that lingo in it. Oh, I forgot to show you something. On the other slide, did y'all notice there were things like this? I don't know if y'all noticed that. These two notations mean the same thing, okay? And I'll go through that later. If you see this, they're talking about some sort of permutation or combination, and they're just not writing the letter in front of it. I'll teach you that later. I'll show you how to punch all this into your calculator too, but right now you don't need it. All right, a to the 8th, what's the next one to be? 7, 6, 5, 4, 3, 2, 1, none at all. You add a couple of more a plus b's to the a plus b to the 6th or x plus y to the 6th. I don't even think I have room on the slide to do it. The b is going to start off with 0 and grow until you get to what? 8. Okay, your first and last number is going to always be a 1. I don't know if I should go back to the last slide. Let me show you this. Again, I'm just always actively looking for patterns to help me out. Do you see how these were 1s? That'll always happen. And do you see how the next one, see the 6 power? The next to last one were 6s as I'm coming in on my up and down thing. Okay? So you could actually use the little pattern that I showed you, but these are going to end up being 8s. So this number is going to show up next right here. You could verify that with 8 factorial over 7 factorial, 1 factorial. Wouldn't that just leave you 8? Okay. Then this one I'm going to have to figure out. This one right here is going to be 8 factorial over what? 6 factorial, 2 factorial. So that's 8, 7 over 2, 1. That's 56 divided by 2, which is 28. Is that 28?
Yeah.
Is that 28? Okay.
Yeah, because it'd be 8.
And this one's 28, right? Okay. And then 8 factorial, keep using this number. I didn't explain that very well in the last slide, I'm sorry. This number is on the top and the numbers on the bottom are created, you've already created them. So this one's going to be 5 factorial, 3 factorial. 8, 7, 6, 3, 2, 1. That one's 56. And this one's 56. So then I need 8 factorial over 4 factorial, 4 factorial. 8, 7, 6, 5, 4, 3, 2, 1. 4, 3, 2, 1. 3, 2, 1 is 6. 70. And then you could write it out in a string. You can also check these on, and by the way, a big part of the point of the class today is looking at how big bad formulas can look. Also, I'm going to get to Pascal's triangle. Some of y'all notice these numbers down here, 1, 6, 15, 20, 15, 1. You know, if we were going to meet 15, 6, 1, those numbers, there was a man's Pascal that you may have heard of that actually realized this triangle does a whole lot of cool stuff. It even has the Fibonacci number somehow built into it. It's amazing. But Blaise Pascal, I wish my name was Blaise Mazeri. But anyway, you also can pull the numbers out of this. And I'm well aware of that. A lot of people are usually raising their hand, can I just use Pascal's triangle? Yeah, you can. I just don't like writing the triangle out to 8 rows. It gets pretty big. I mean, so I'm okay with what I'm doing because the pattern collapses on itself coming and going. But I'll teach you this later, okay? If we were going to be at school Thursday, I would teach it to you then. Now, next, I don't know what else I wanted to say. Girls, that changes if you do something like x minus 2y to the 4th. So if you kind of phased out because it was easy, please watch. First of all, the binomial theorem is only taught with a plus And so all that we noticed, it needs to be a plus. So I need to stick the negative with the -2, okay? If you've ever multiplied x minus y to some power, the signs alternate back and forth. You can do it later. I'm going to keep moving, okay? Also now, do you see this 2 is going to get caught up in that exponent? So it's going to be different. So I'm going to start off with my first term to the 4, 3, 2, 1, 0. My second term is -2y in parentheses, because the exponent is going to apply to the entire back term. This is going to go 0, 1, 2, 3, 4. What are your first and last numbers? 1. And the next ones are going to be 4. And so you only have to figure out 1. And so you still base it on this right now. It's going to be 4 factorial over 2 factorial, which is 6. And then you multiply it out. This one's -2 x to the 4th y. I'm sorry, no, it's not. What's -2y to the 0? So that's just x to the 4th. This one is -8x cubed y. This one, you've got to be careful, is a 6. -2 squared is 4. So that's 24x squared y squared. -2 cubed is -8 times this 4. So I get -32xy cubed. And then it ends, that's 1. It ends with 16y to the 4th. So do you see your numbers in here can affect what happens now? We don't have such a cute little thing going on, okay? I didn't do one that actually has an exponent within it, but you still do the same thing, but then you just figure it out as you go. Okay, now, I'm going to use my last minute to show y'all something. So what if I have 3x minus y to the 10th? And girls, listen, hold still. I'm going to hurry. I'm not going to see for a long time, okay? What if I have 3x minus y, and on the test or on the homework, I just ask for the 6th term? Because I can find out if you know what you're doing just by not making you do it every time. So this is what I would say let's do. Let's go 3x. I would count on my fingers to make sure I counted right, kind of like our sequences and series last time when we messed this up. I don't want to write them all down. I'm going to go 10, 9, 8, 7, 6, 5. 10, 9, 8, 7, 6, 5. And so this one's going to be 3x to the 5th, -y. Now how, I don't need to count up. Somebody in the room notice what these have to add up to. So by default, what's that? 5. My coefficient's going to be 10 factorial over what? 5 and 5. So do you see you can jump in and find any term, which you'll see is important. All right, I'll post your homework when I decide exactly what all it's going to be, because now my syllabus is all messed up.
Thank you.
Happy spring break. Lindsay, I'm sorry I didn't answer your question. I was trying to cram a lot into it.